Hey there, space enthusiasts. Today we're diving into the mind-bending world of space-time. Buckle up, because these 10 fun facts are going to take you on a cosmic journey. We're about to explore how space and time are intertwined in this fabric. A four-dimensional playground where massive objects can make time run slower. Gravity is just a curve in this fabric. And black holes exist. Ready? Let's warp speed ahead. Imagine a trampoline. Now picture this trampoline as the fabric of space-time. If you roll a tennis ball across it, the ball goes in a straight line, right? That's like a beam of light traveling through space. But here's where it gets interesting. If you put a bowling ball in the middle of the trampoline, it makes a dip, a curve. Now roll the tennis ball again. It no longer goes straight, does it? It curves around that bowling ball. That's gravity at work. Massive objects like our sun warp the fabric of space-time around them. The more massive the object, the bigger the warp. And that warp is what we experience as gravity. General relativity, Einstein's masterpiece, tells us how matter and energy interact with this fabric of space-time. So next time you see an object falling, remember it's following the curves of space-time, just like that tennis ball on a trampoline. Remember how I said space-time is a four-dimensional playground? Well, one of the wildest things about this playground is that time itself isn't the same for everyone. It's all relative. Imagine two identical clocks, one here on Earth and another on a spaceship zooming past us at close to the speed of light. According to Einstein's theory of special relativity, time on the speeding spaceship actually slows down relative to time on Earth. The faster you go, the slower time goes. This time dilation effect also happens near massive objects. The stronger the gravity, the more warped space-time becomes, and the slower time runs. Time on top of Mount Everest actually runs slightly faster than time at sea level. This mind-bending concept has huge implications. GPS satellites, which rely on super-accurate timekeeping, have to account for time dilation to function properly. Time dilation is a real phenomenon, confirmed by countless experiments. Black holes, those cosmic monsters that lurk in the darkest corners of the universe. These are regions of space-time where gravity is so strong, so intense, that nothing, not even light, can escape their grasp. Imagine that trampoline again. This time, you drop something incredibly dense, something so heavy it rips a hole straight through the fabric. That's kind of like what a black hole does to space-time. These gravitational behemoths are formed when massive stars collapse at the end of their lives. The remaining core gets squeezed into an infinitely small point called a singularity, a point where the laws of physics as we know them break down. Surrounding this singularity is the event horizon. Once you cross the event horizon, there's no turning back. You're trapped forever within the black hole's gravitational grip. As you fall into a black hole, time itself gets distorted. Black holes offer a glimpse into the extreme limits of physics, where space, time, and gravity collide in a cosmic dance of unimaginable power. Remember those ripples in the fabric of space-time we talked about? Well, those ripples are real, and they're called gravitational waves. Einstein predicted their existence over a century ago, but it wasn't until 2015 that we finally detected them. Imagine two black holes locked in a cosmic waltz, spiraling closer and closer together. As they do, they stir up space-time, sending out ripples like waves crashing on a cosmic shore. It took LIGO to finally pick up the signal from two black holes colliding over 1 billion light-years away. Now we can listen to the universe, to the symphony of gravitational waves, and uncover secrets about the most violent events in the cosmos. We've all heard that nothing can travel faster than the speed of light. Light travels at an incredible speed, about 299,792,458 meters per second. That's fast enough to circle the Earth over 7 times in just 1 second. The speed of light is more than just how fast light travels, it's woven into the very fabric of space and time. Einstein showed us that space and time are intertwined. As you approach the speed of light, time slows down relative to someone standing still. The speed of light is a fundamental constant that defines the relationship between space, time, and the very structure of the universe. Wormholes are one of the most intriguing and mind-bending predictions of Einstein's theory of general relativity. These cosmic shortcuts offer a tantalizing possibility of traversing vast distances across the universe in the blink of an eye. Imagine folding a piece of paper in half. Now imagine that the paper represents the fabric of space-time. A wormhole is like a tunnel connecting two distant points on that folded piece of paper, a shortcut through the higher dimensions. Theoretically, if we could create or find a wormhole, we could travel through it to reach distant galaxies in an instant. Of course, wormholes remain highly theoretical, and there's no evidence that they actually exist. But the idea of wormholes captures our imagination because it suggests that the universe might be even stranger and more wondrous than we can currently comprehend. It's the ultimate cosmic origin story, the event that birthed our universe. But forget everything you think you know about explosions because the Big Bang was anything but. It wasn't an explosion in space, it was an expansion of space itself. Imagine a tiny, infinitely dense point smaller than an atom containing all the matter and energy of the universe we see today. Then, about 13.8 billion years ago, this point began to expand. Space itself stretched and inflated, and as it did, the universe cooled and evolved. Subatomic particles formed, then atoms, stars, galaxies, and eventually planets like our own. The Big Bang wasn't just the beginning of matter and energy, it was the beginning of space and time as we know them. The Big Bang model is supported by a mountain of evidence, from the cosmic microwave background radiation to the abundance of light elements in the universe. So the next time you look up at the night sky, remember, you're looking back in time, toward the faint afterglow of that ancient explosion of space and time. Imagine looking back in time to a time just 380,000 years after the Big Bang. What would you see? Well, you'd see a faint glow, a faint afterglow of the Big Bang itself. This glow is called the cosmic microwave background radiation, or CMB. This faint radiation, discovered in 1964, is like a baby picture of the universe. The CMB is incredibly uniform, with a temperature of just 2.7 Kelvin, or about minus 455 degrees Fahrenheit. Studying the CMB is like looking back in time to the universe's infancy, allowing us to study its earliest moments and understand how it evolved into the complex and wondrous cosmos we see today. Time travel, it's the stuff of science fiction, right? But could it actually be possible? According to Einstein's theories, the answer might be a mind-bending yes, but with some serious caveats. We've already talked about how time is relative, how it can slow down near massive objects or at high speeds. But what if we could manipulate space-time in such a way as to create closed loops, allowing us to travel back in time? One theoretical possibility is the existence of wormholes, those cosmic shortcuts through space-time. So, while we might not have time machines zipping around just yet, the possibility of time travel remains an intriguing and mind-boggling area of scientific inquiry. The universe is expanding. It's not just that galaxies are moving through space, space itself is stretching, carrying galaxies along for the ride like cosmic surfers on a wave. This expansion was first observed by Edwin Hubble in the 1920s, and it has profound implications for the fate of our universe. As space expands, galaxies are moving farther and farther apart. Think of it like dots on a balloon. As you inflate the balloon, the dots move away from each other. The expansion of the universe is accelerating, driven by a mysterious force called dark energy. We don't know what dark energy is, but we know it makes up about 70% of the energy density of the universe. The expanding universe is a reminder that we live in a dynamic and ever-changing cosmos, a universe that's full of mysteries waiting to be unraveled. Thanks for joining us on this incredible journey through space-time. If you enjoyed these fun facts, don't forget to like, subscribe, and hit the bell icon for more mind-blowing content. We've explored the fabric of space-time, delved into the mysteries of black holes, and pondered the possibilities of time travel. But most importantly, I hope you've come away with a sense of wonder and awe at the sheer scale and strangeness of our universe. Keep questioning, keep exploring, and keep looking up at the stars because the universe is full of wonders waiting to be discovered. Until next time, keep those brains sparking.